Welcome to qnawire.
We have a harmonic oscillator. We're given a solution for the wave function for the first energy level, the 0th energy level rather. And we're asked to plug this into the time-independent Schrodinger equation and see if it's a valid solution. So starting out, we have the time-independent Schrodinger equation, negative h bar squared over 2m, second derivative in space of our wave function, plus the potential, which in this case is 1/2 kx squared, wave function, equal to E naught wave function, psi. So it's one way that's suggested, and this is in the chapter, is to reformulate this into the form psi double x derivative equal to negative or positive 2m over h bar squared, 1/2 kx squared minus e times psi. So this is just a little bit of a simplification. So obviously we're going to have to take a couple of spatial derivatives of this wave function. So let's start off with that. So the first derivative, because we're only dealing with a exponential, we will bring it down just using a kind of a chain rule. Nothing too bad. Root mk over h bar times x. That's our chain rule. And then we have the original 2h bar x squared. Okay. So if we take another spatial derivative, and there's no dot here, so that's just an x. If we take another spatial derivative, we have to do a product rule and a chain rule. Once that's figured out, we end up with negative root mk over h bar. And then it's just the same stuff, the original wave function. I'll just put that in blank parentheses. And then we have a second term, mk h bar squared, x squared, and then times the original wave function and everything. So that's it for the second derivative. Now we can set these two sides equal and see what we can do, see if we can get them to be explicitly equal to each other. So after substituting everything in, we have the original wave function, which I'm just going to say is that, so we don't have to keep rewriting it over and over again. mk over h bar plus that second term, mk over h bar squared, x squared. And now our right-hand side of that equation, which I showed, right, so there's not much we can really do to the left-hand side anymore. It's basically as simplified as it can get. We can divide out the wave function from both sides. We can divide psi away. And so what we're going to do is we're going to work on this right-hand side to try to get it to look like the left-hand side. So here's the right-hand side only. First step we can do is we can expand this all the way out. We will end up with mk h bar over h bar squared, x squared. That looks pretty familiar. And then we have another term, m omega over h bar. That looks a little bit less familiar. However, at this point, we can use the fact that omega equals the square root of k over m. That's just from classical mechanics. We can throw that in there. And then once we start dealing with this, we can turn that second term into something more recognizable. And we'll finally be left with mk over h bar squared, x squared, the one term we recognize, minus the other term we recognize, just doing a little bit of square root math. All right, so I have the right-hand side, which looks just like the left-hand side, which means it must be true. And that's it.